already 6.
All right.
Wait a minute, we got a relegate.
So, 12:05. Well, it's 12:04 now. I guess we might not work for a second before we can just start. All right, we're going to talk about beta stuff. Yay.
Yeah.
All right, so talk about probability and Bayes nets. That'd be great. Let's talk about exhaustion first. Who knows what exhaustion is? You actually know.
You're tired
Alright.
and it's like you want to go to sleep.
So, in 6034, exhaustion is
I feel it every day.
basically if like you take all of the possible probabilities for all the possible values of a variable, they should add up to 1. So if A is Boolean, then the probability that A is true plus the probability that A is false should be 1. Also known as probability of A plus probability of not A equals 1. And then if it has 3 values, for example, so more than 2, then the probability that A equals A1 plus probability that A equals A2 plus probability that A equals A3 equals 1. So this holds when A is the hypothesis in the candidate probability, but it doesn't work when A is given in the conditional probability. So what that means is that probability.
Can you say that again?
Yeah, so let me write it on the board first. So probably so if A is like a dependent variable, so say that A equals A1 dependent on B equals B1, plus probably that A equals A2 given B equals B1, plus probably A equals A3 given B equals B1 equals 1. So if you go across, so the probability that A equals is 3 values given some value of B equals 1, but like probability that A equals A1 given B equals B1, plus probably A equals A1 given B equals B2, like if you vary the given rather than the dependent, or if you vary the given at all, then this is not necessarily true. So I don't know what candidate probability, conditional probability, I can't read. Okay. So yeah, so it holds so this whole exhaustion holds for the hypothesis in the conditional probability, but it doesn't hold for the given.
So in a sense, you can think of the given thing as like its own probability space. That's just like, or that these things are say, well, forget it.
Yes, true.
That is yes.
Yeah.
I forget. Will students know all about like conditional probabilities, like what probability of A given B is?
If they went to lecture, they will.
Okay.
Yeah. In lecture, Winston talks about like the training rule and stuff like that, or I'm assuming he will. We've talked about it the last 2 years. So.
Even this notation. I mean, I assume that they should know it from like 602 or something.
But that's not, so 042 is not a prereq technically,
Well,
but
601 isn't our thing anymore.
yeah.
Should we give like a short example, like the probability if it's raining or if it's cloudy?
So one of the lectures is a crash course in probability.
Okay.
So they should have gone to lecture and like, if they don't know probability at all, they should have like seen it all already.
Okay.
But if you look at your students and realize that they have no idea what you're talking about, then yeah, it's a good idea to like go back and be like, by the way, probability works like this. Yeah, there's also like a note on here talking about like a flowchart between joint, marginal, and conditional, but I don't know what that means, and it's not expanded upon, so I'm ignoring it.
Wait, what are those words?
Joint, marginal, and conditional? Yeah, they're, so like types of probability.
Well, it's saying that the marginal probability is like, I'm trying to remember the way it would work exactly. There is an equation.
Yeah, so joint is like probability of A and B.
Oh, okay.
Conditional is probability of like A given B, and what's marginal?
It's it's like if you sum over all of something, you should then have
Yes, I
like
thought
every.
that
Oh,
was
like P of
something
A
like
or something, given
Yeah.
P of A given. Okay.
So there's
Well,
possibly some more
we gotta
information,
learn this quick.
but we're pretty much ignoring that for now.
Cool.
Is that like a thing they could be asked about marginal probability? or
So
something?
there's a second, like kind of, but there's going to be a second recitation on Bayes stuff. So we're going to
Okay,
cover
so
a lot of the
that's-
Bayes stuff in this recitation, and then we'll cover it more in the next recitation. And then, like after the next meta, we'll decide which stuff should go in which order. So we're just going to try to cover as much as we can now, and then finish covering it next meta, and then decide what to put where. Okay, so that's exhaustion. Let's talk about independence. Exhaustion and
You
independence.
need to know data, right?
Yeah.
So there's the Merlin data set
And
from Harpies.
I can't spell, but you understand what I'm saying. Close enough. Okay, so independence is the idea that knowledge of one doesn't affect the knowledge of another. So A is independent of B. So that means is independent of. If and only if probability of A given B is equal to the probability of A. That make sense?
What is that symbol?
Is independent of.
No, I mean, what is it? It's two parallel lines with a bar.
Yeah, it's like an upside down capital
Oh,
Y.
okay.
Yeah. Oh, so that's marginal independence.
That's marginal independence, but it's not marginal probability.
No, but it's marginal independence.
Yeah.
Okay.
Class
And,
on this like last year. I completely forgot all of it.
That's okay, last year.
008.
yeah. Cool. And then so we also have that probability of A and B. be equal. So by the chain rule, that's equal to the probability of A given B. That's probability of B, which is probability of A times probability of B if they're independent. So because this is true, that means probability of A and B is equal to probability of A times probability of B if A and B are independent. Or if A is independent of B.
Yeah, does this follow from?
Yeah, it follows. So this
Bayes rule and that's
is Bayes' rule. And then goes that way by independence.
Okay. So when we write probability of A and B, is it the same as A comma B? Is that the same notation?
Yeah, I guess.
probability. Yeah, it's
I've seen A comma B.
it's
Okay,
either
it's
Yeah.
the same, right?
We'll just use
Joint
AB.
probability.
Okay.
Yeah,
A and B.
yeah. Cool, so that's marginal independence. Now let's talk about conditional independence. So A, I don't know where to stand, so you guys can't see wherever I stand. So A is independent of B given C. If and only if probability of A given BC is equal to probability of A given C. Which follows that probability of AB given C is equal to probability B given C times probability, oh, I think there might be an error here, but I can't tell. There's an error in the notes somewhere and I forget where they are, but we'll find them. Yeah. Does that make sense? Looks legit.
Quick thing, that second probability of A, B given C,
Yeah.
isn't that the same thing that you wrote on the left side?
Yep, that's where the error is. Ha!
So again, the second line is assuming that A is independent from B given C. or-
Yeah.
Okay. So,
And the middle one, it says P of A bar B C. Does that mean P of A given like both B and C together?
Yeah.
so are we just gonna be just like giving this to them, like, all right, guys, here are all the rules, just know them, or like should there be some? It would be very annoying, I imagine, to have
Yeah.
to explain the logic behind every single thing.
Well, they should have gotten a lot of it from lecture.
Okay.
Yeah.
I guess we'll ask this means.
Yeah. So and then this can like be expand. So they should have actually seen, I think, most of this in lecture, and then we'll still go on and talk about chain rule too from this, which is when you have like probability of A given C, D, E,
Oh, yeah.
you can equal that to like, you can chunk it up, break it up,
No,
so you
yeah.
don't have one giant probability. Okay. Cool. So using this, you can reduce the number of parameters needed to calculate joint probabilities. So here you need to know like A and B given C, which like requires a lot of knowledge about their various probabilities. But here you just need B given C and A given C. And similarly up here, you need to know all about A and all about B. But here you can just know probability of A and probability of B. So we'll see that as an example, if there are two, there are two Boolean variables and no independence assumptions. How many parameters do we need to describe that? To describe their full like joint probability.
You say parameters.
So for example, if we have I don't know where to stand because it's hard to see wherever I stand.
Just sit on the floor.
So how many numbers do we need to describe the probability of like A and B, I think that means?
It'll be
Yeah.
4, right?
So
Well, if
do we
they're-
need 4? So
If
A,
they're independent, you would need.
Oh, if they're independent or
If they're-
dependent?
If they're not independent,
Well, there's no assumption on anything.
no independence, right? So wouldn't that mean that you would need like? How could you know that?
No, it's just 4, right?
almost. So if you know
Oh, yeah,
these three
3.
numbers, then this is 1
Exhaustion.
minus the sum of those 3, right? Because of exhaustion. So you need 3 parameters. What if there is independence? How many parameters do you need?
1,
2. Yeah.
2.
Yeah. So you can't like use exhaustion because you need to know probability of A and probability of B. You can't use exhaustion to like scale that down at all. So what if we have 100 Boolean vars with no independence? I don't really want to draw that giant table. So how many numbers do you think we would need?
2 to the 100 minus 1.
Yeah, exactly.
Can we go back to explaining previous
Literally, because you just need to.
with independence? Yes.
With independence, yeah. So if you want to know probability of A and B, then you just need to know probability of A and probability of B.
Okay, but what if you,
Yeah, and you can't use exhaustion. Like if you know probability of A, there's no way to figure out the probability of B if you only know B of A. Yeah. Are we good on that? Okay. So does it make sense why if we have 100 Boolean with no independence, we need 2 to the 100 minus 1 parameters? And then what if they're all independent? How many parameters do we need? Yeah, 100, exactly. Yeah. Does that make sense what those numbers mean? So this would be like probability of A, B, C, D, whatever, and probability of not A, B, like not A, and then B, C, D, and then probability of A, not B, C, D, like all possible combinations.
Just a random point of clarification. When you're saying parameters, right?
Yeah.
The first example, you're saying that you need to know what this joint like 3 entries in this joint probability table are,
Yeah.
right? But when you say for is independent, you just need to know probabilities of A and B.
Yeah.
Like, you know, A equals T, B equals T, and then
Yeah.
you can calculate everything, right, as a result. So in saying that, this was like just any number you could possibly need. So
Yeah.
for the all independence case over at the 100, you're just saying you just need to know A equals T, B equals T for like
Yeah.
everything else.
Yeah. So by parameter, I mean like how many numbers do you need in order to fill out the whole joint probability table? Yeah.
So, or if we go back to the independence of two cases, if you said, you know, we need P of A and P of B, but what if we only knew like P of A equals false and B equals true, and like P of both false? Can we still do the four?
Well, if you know the probability of A equals false, doesn't that give you the probability of,
Oh,
yeah.
Okay. Got it.
Any other questions on that? Awesome. Let's talk about Bayesnet. Can I erase this stuff? No.
Just be very fast presentation. Actually, no, probably very long.
Again, students should have seen Bayesnets in lecture, but it'll be much more new to them than probability, so we'll go over it. So the basic idea behind Bayesnets is that we're gonna draw images to, draw nets to show what variables are dependent on each other, and then use that to figure out how many parameters we need and which parameters we need. So there's a couple of assumptions. Each variable is conditionally independent of its non-descendants given its parents. So what it's going to look like is if we have some variable C, A, and then C will go down to like D and E. So basic assumption, so each variable is conditionally independent of its non-descendants given its parents. So what does that mean? That means that the probability, oh, I missed a couple. So if we're using this guy here as an example, Bayesnet, that means that the probability of F given parents of F and the non-descendants of F is equal to the probability of F given parents of F. So who are the parents of F?
C, E, A, and B.
No, we just look at like one layer parents, we don't care about ground parents.
Direct
Yeah, so direct parent of F,
no.
D. Non-descendants of F, yeah, everything except for G. So A, B, C, D, E. So anything that's not a child, grandchild, great-grandchild.
Right.
Yeah.
Can I see what the word looks like? Oh, we didn't, right? But.
So that means that probability of F given D, A, B, C, E is equal to the probability of F given D. Yeah, cool. So can you tell, is A independent of B given D and F?
have any parents, which would suggest then that it is, that would suggest it's actually completely independent from everything else, so from B, so then
Yeah.
if it's a dependent of B, then it doesn't matter.
Yep. Exactly. Did I say it right?
What was the question?
Is A independent of B given D and F? Right, TBH, I don't know the answer to this.
Oh, really?
Yeah.
So we actually don't.
It'll be in the notes that Jessica will email out.
I'm thinking of a situation that I could be wrong here.
Is independence,
Is it where like C doesn't
two-way,
actually
right?
have
It's
an
symmetric?
effect on the
I think so, yeah.
Not sure.
Oh, wait, no. Because A can like be independent of C, but C depends on A,
Right,
right?
okay, so
Yeah, so it's not symmetric.
I just don't recall that if two things are just marginally independent, if that means that given anything, they're also independent from that. I feel like
Yeah.
that isn't necessarily true, but I feel like it kind of would have to be for this.
So I guess we can use that, right? So is the probability of A given B df equal to the probability of A given df? Is that true? So we can find that out by eliminating the non-descendants from the givens, right? So which ones are non-descendants? Yeah.
I should know.
So B's non-descendant, so is that true? Yeah. Okay, cool. So it's true. Good. We figured it out. We did that.
So what did you do?
So I used this equation
Okay.
to rewrite this equation into this.
Thanks.
And then once I had that, I crossed out any non-descendants and then checked to see if they were equal.
Oh.
A very interesting lesson.
Yeah.
We crossed off the non-descendants because of something up there.
Yeah, because of the base net assumption. All right, so let's talk about D-separation. So D-separation is how we're gonna find out if things are dependent on each other without being confused by math. Math is hard. So side note, D stands for directional, but we'll just keep calling it D separation. So first we're gonna draw the ancestral graph. Thanks. Cool, so we'll draw the ancestral graph. So if we want to find out if A and B are conditionally independent given D and F, then we can follow this method as well. So draw the ancestral graph. Oh no, why is it not on here? Okay, that's fine. So we'll draw the ancestral graph by putting this is a mess, sorry. So we have to put on everything that is in our question, I guess. So we need A, B, D, and F. And then all of their ancestors. Okay. And then we will moralize the graph by marrying parents.
What?
Yeah, we'll get to it in a second.
Why do they use the word moralized?
Because you're marrying parents. Because if they have children and they're unwed, they're living in sin.
I think
Don't
that's
you know
actually
that?
true. I
Come
think
on,
what he's
man.
saying is right. Okay. So
I mean, that's the only way to get that.
basically now, where do I stand? Why is it
Do you want to remove this? Does that help?
No, yeah, all right. Okay, so there's these two parents which are not connected even though they have a child, so we will connect them. And then we will disorient the edge by marrying in quotes. Disorient edges, aka make them bidirectional, So we'll just take off the arrowheads. Awesome. And then delete givens and their edges. So what are the givens?
D and F.
Yeah. So we get rid of D and F and their edges. So now we just have A, B, C here. And now we can read the answer off the graph. If they are disconnected, then they're independent. And if they're connected, then they're dependent. But dependent has an asterisk there because they're only dependent in like by Bayes nets. They might still be like they might happen to be independent numerically. So they're structurally dependent on each other, but they because of like some fluke of how the math works out for this problem, they might be numerically independent or independent in some other way. So we can prove that if they're disconnected, then they're definitely independent. But if they're connected, then they may be independent still.
Wait, is
If
that
they're
what?
connected, then that's
Working on it. I'm working on it. Let me see if I can find my notes from last year and draw a better graph. Yeah, so that should maybe be. So it's possible that that just means that they're numerically. So structurally they are dependent, but numerically we can prove that they're independent.
What is D again? The D separation?
Directional.
Directional.
Directional. Yeah.
Thanks.
That's fine.
We're gonna need to call someone in on this.
So what is, because we're asking is A independent from B given DF, right?
Yeah.
That's our question.
But they are now connected.
It would actually make sense if you're saying that because G and F have A and B as their ancestors, that for some reason you take now them into account, which would be some relation.
Yeah.
That's what it seemed like. That would, on some level, make sense. But
Yeah, they're
Yeah,
like not
so this is
independent
right.
anymore because
given because it's their child
Yeah.
that's being like tested there.
So the graph, that is how you do D-separation. So they are structurally dependent. Maybe I did the math wrong over here. I'm realizing now that the reason that was on the notes is because we're asking that question and then we won't solve it numerically, we'll just solve it structurally. So you just ignore that.
So are we looking, we're looking for the connection between A and B? Is that the final?
Yeah, so our question is A independent of B given D and F? And since we do the ancestral graph and we moralized, destroying the edges, and then deleted relevant edges, and now since A is connected to B in this like final D-separation graph, then A is dependent, like A and B are not independent.
do you marry them
Structurally.
first though? Because then even if you deleted every child, you would still have a thing, wouldn't you? Right? Because you
What do you
drew a line between A and B.
Yeah,
If everything else was given, then right, you would cross
Well,
everything out and they would still be connected. Like
if
how would
B,
you?
so if B was given, then you would
Oh, if
cross
B
it out,
was
right?
given.
Yeah.
But A independent of B given B is like a
Yeah.
like
So wait, can you say your question again?
no matter what you put in a given there, aside
Yeah.
from A and B, which would make it a weird question, like is A independent of B given B? Like what?
Yeah.
They're going to be connected because you could delete all the kids and the Mary is still there.
Yeah, but so
We're-
if you had B down here instead, right?
Yeah,
wouldn't
then
be
it would be
connected.
something
Yeah.
different.
So because they're both parents to the same node.
So then but so even if you knew every child, you would still they'd still be dependent.
Yeah. According to this.
Wait, so we just do the short example of A independent of B given C?
Yeah, sure. So A independent of B given C. So we would draw A, B, C, more or less a graph by marrying parents, disorient the edges, and then delete the givens and their edges. So we delete C and those edges. So now we just have A connected to B. So A is structurally dependent on B given C.
On some level, that doesn't actually make sense.
Yeah.
Yeah, I feel like the
So-
marry edge, because
Yeah.
the marry edge is caused by C, it seems weird that it's, right?
So let's do like a more,
It's like-
so let's consider an example where like, that might make a little bit more sense. So if you, for example, have, so the idea with this is called explaining away. And basically, if you go to the ER, say that there are two types of people that go to the ER. Some of them have the flu, and everyone else is going because they have a broken arm. So, given that you're in the ER, like if you have the flu, depends on whether or not you have a broken arm, right? Because you're probably not going to go because you have a flu and a broken arm. So if you know something about whether or not a person has a broken arm, that tells you information about whether or not they have the flu.
Cool.
So we know that A is independent of B if you're not given anything. But A independent of B given C.
Why is that true? If you draw the parent line and then don't delete anything, they're still connected.
Because you don't draw C at all. You would just draw A and B.
Oh, I
There's
see.
no
You only
ancestors.
draw the thing. I see. Okay.
Yeah.
Oh, okay. Now that
made
resolves
it
my
clear.
question.
That made it clear to everything.
Because I was like, if you draw everything, then they're connected no matter what. But okay.
Yeah, you just draw the letters that are like involved in your question and then their ancestors.
Okay.
Yeah. Cool. So A is independent of B. We learned earlier A independent of B given the F is not true. A independent of B given C is not true, and it's called explaining away. Do those three make
Do you
sense?
mind explaining away thing one more time?
Yeah. So say that there are two kinds of people that go into the ER. They either have the flu or a broken arm. Like if you have the flu, there's some probability to go to the ER. Broken arm, there's some probability of going to the ER. So if you see someone in the ER, and you like notice if they have a broken arm, then that tells you something about whether or not they have the flu.
But well, it's just that if you have given C, doesn't that mean all the information you would have is that they are in the ER? Just like I'm not sure how you would have the broken arm information as well. In that.
Well, it's just that. So independent means that knowledge of one variable tells you nothing about the other, right? But if you know C, and then you gain some knowledge about either A or B, now you have more information about the other A or B.
I feel like this example is because, right, like you're saying, oh, if you're in the ER, it's unlikely you both have the flu and a broken arm, but like,
Well, it's
Yeah.
possible.
in general,
Exactly.
right, in general, it's unlikely you both have the flu and a broken arm, like, I don't know, right?
Well, probability-wise, that it works out. It's,
Yeah. I mean, like, you could replace
Yeah,
the
yeah,
ER
why
with
not?
the world if you want, but
Yeah, but then what does given the world mean?
Well, that's a
So-
completely different question.
Well, look, I get why the
Yeah.
connectivity of the graph, I get why it works. I'm just saying, like, intuitively, the
Yeah.
example is kind of weird. I don't know.
so like, there's. I
Like,
guess
it's
the-
almost like, I
yeah.
like, you know, like the grass is wet thing or something, and like the sprinkler versus the rain.
What?
I don't remember the exact. It was something. It was the same thing as this, but it was different words in the bubbles. And I thought it made
Okay.
more sense.
I have a vague memory of what
I
you're
think it would be
saying.
the grass is wet for the ER, then the sprinkler and the
Yeah,
rain.
well, yeah, that might
Oh, okay.
So it's a very similar structure. I think it's the same explaining away reason for why it works. So basically, if you see the grass, normally it's the same probability if it rained, like whether the sprinkler ran tells you, or whether the sprinkler ran tells you nothing about water. But if we know that the grass is wet and we know that the sprinkler ran, then that's a good explanation for why the grass is wet. So we don't have to go to it.
Yeah.
Sure. Is there still confusion about this?
I still feel like the intuition doesn't fully make sense. It might just be the example, right? If you're just saying.
Do you want me to replace it with the grass as well?
No.
Example?
No. It's just right. If you're saying that A and B are independent, right?
Yeah.
This means you said right. Knowledge of one shouldn't affect the other.
Yeah.
Or, right. It's just unclear why them being in the ER would then somehow give you more knowledge about those two things.
Yeah.
You're not.
So usually you go to the ER if you have like one thing wrong with you that you need fixed, right? Where like in the world I feel like it's sort of equally possible that like people with broken arms get sick sometimes, right? But if you're going to the ER, it's probably because you have one thing that is like seriously broken. I guess. So like broken arm, does it make sense to say broken arm uncasted? So if you have a broken arm without a cast,
Okay, sure.
does that make you feel better?
Well, it's just that like if you think of each of these things, right, it's just
Yeah.
like a true or false value, right? And all I know is, ER equals true. Then it's like, so how does that assist me in knowing? I guess, how does that assist me in knowing one over the other? Like in this case, wasn't that like I'm not. Sure.
I think it's because like flu has some probability of going to the ER, and broken arm has some probability of going to the ER.
Oh, okay. Yeah, I'm kind of weighted in that. Maybe,
Yeah.
Maybe that's the thing.
Yeah, I think the thing that we're missing is
That
that
should already be like a conditional world, like a
yeah,
probability
the
in the
conditional
world.
of A given
Yeah.
C, and we're like just kind of forgetting the given C.
Yeah,
We're
that
just
should
doing
be
the probability.
That should be in there. Okay.
Yeah. All right. I'm gonna assume that we know what we're talking about now. Okay. Can I erase this
We'll
stuff?
find out next week.
Yeah.
Well, we're not gonna find out. We're
Next-
gonna go
next
over this
week.
again next week. Yeah, in next meta. Yeah.
We got some time.
Because the recitations that we're teaching, like next Monday, Tuesday, are reviews for quiz 4. So you're not teaching this next week.
I know. I was like a review recitation, a purely review recitation.
Or quiz 3, right?
3, whichever one's happening soon.
It's just neural nets and parts.
Okay, so
That's the
today
easiest topic, and it's like whatever.
we've got some Bayes net that looks like this.
So you got some neural nets, like double lines. Okay. It's like some SVMs with those nets.
And we want to know probability of A, and we want to know probability of, so what is the probability of C dependent on by this graph?
A, but also,
Yeah.
is there between A and B, is there a directionality there?
Thanks. And then D has 2 errors going into it, so we need a probability of D given A, B. And then E, we need the probability of E given C, D. So how many parameters do we need, like, total overall to find out all the parameters of A through E?
Seems the original.
Yeah.
So we need P of A, is that right?
Yeah, so we need P of A, that's 1. Do we need any more, do we need more than one number to describe the probability of A? No, we have one number up there.
We always assume these are like Boolean, right?
Yeah, sorry, these are all Boolean. How many numbers do we need to describe C? I have 3 and 2. Which do we think?
Maybe.
So my reasoning for 2 is we need the probability of C if A is true and the probability of C if A is false.
Oh, that's fair. That's fair.
Yep, exactly. So 2, because we have A, probability of C given A, true, false. So we need some number there and some number there. How about, oh, I forgot probability of B. How many do we need to describe probability of B? 1. How about probability of D given AB?
4.
Why 4?
Just because you just want to know like for every possible combination of A and B, you just need to know A is T, B is T, A is F, B is
Yeah.
T, etc.
Exactly. So A, B, probability of D given A, B. So we need true, 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 false, true. Oops. So we need 4 numbers there. Why can't we use exhaustion to get rid of one of those?
Because they're given to all be different.
Yeah,
Have the same
exactly.
probabilities.
Because the givens change on each row, so we can't use exhaustion to just have 3 numbers. So we need 4 here. And how many do we need here? 4, yeah. Okay. So how many is that in total?
Well,
12. So,
I didn't count.
so if I just said that we have 5 Boolean values, how many parameters do we need to describe them? What would you say? If they're like not all independent of each other. Like if you didn't know that this is the dependence relationship, how many parameters do you need?
31
31, right. So,
minus.
oops. 2 to the 5 minus 1 equals 31. So we made a pretty big reduction. We made a pretty big reduction in how many parameters we needed to know by utilizing this dependency graph. Okay. And also, quick note, from here you can get the probability of C given A, and if you do 1 minus that, then you have the probability of not C given A.
Yeah, I'm just trying to tell them.
Probability of not C given A equals 1 minus probability of C given A. So note that we're getting, so even though we're just listing probability of C given A, you can also calculate probability of not C.
So when you say probability of C given A,
Yeah.
implicitly means probability of C given some assignment, right? Not
Yeah.
probability of C given A equals true.
Say that again?
Because we want to know probability of C
Yeah.
given any possible assignment of A.
Yeah, so this means the probability that C is true given that A is true here, and this is the probability that C is true given that A is false.
Right, I guess the notation is kind of weird, because like
Yeah.
the one on the left you assume is true. Or something.
Yeah, so you can say probability of C is true given
Right.
A.
Okay.
Yeah. Cool. So then, every joint probability can be completed using the values in these tables that we sort of have made. There's another implicit table down here that you could also write out. So, for example, if we want to know what's the probability that A is true, B is true, C is false, D is true, and E is false. So probability of A, B, not C, D, not E. We could then expand that to be probability of not E given A, B, not C, D, times the probability of D given A, B, not C, times probability of not C given A, B, times probability of B given A, times probability of A, by the chain rule that we learned in lecture, right? So you take this and like pull one out and then put the rest of them there, and then take this and pull one out, put the rest of them there. And so now that we've expanded it, we know that a bunch of these things aren't, so we know that E is not dependent on A and B by like looking at its chart, right? It's only dependent on C and D. So you can get rid of these two, get rid of that, you can get rid of B, and you can get rid of that. So by using the chain rule and then getting rid of things that it's not actually dependent on, we can use these 12 parameter values to find the probability of any possible combination.
cross out everything that wasn't a direct parent?
Yeah. Also note that I expanded in topological order, so I expanded from like bottom to top. That is written here as something that you should do. Cool. And then, yeah. So that's everything that you need to know about how to like work with phase nets, and now we're going to talk about applications of them for like 5 minutes. Can I erase this half? Does anyone still want this half? Okay. So we have naive Bayes classification. Small letter. And so basically, we have a graph that starts with y, which is the classification, and the assumption is that the features x1, x2, and x3 are conditionally independent of each other given the classification. So features x1, x2, x3. That says are conditionally and that's going to help us to classify different data points that we want to classify. So if you want to classify something with x1 equals A, x2 equals B, and x3 equals C, then you want to maximize the probability that y equals some classification yi, given that x1 equals A, x2 equals B, and x3 equals C. And this whole thing here is called the posterior. So you want to maximize this posterior over different classifications yi. And so if you take that and then do some fun math with it, that is the same thing as the probability by Bayes' rule of x1 equals A, x2 equals B, x3 equals C, given y equals yi. That is probability that y equals yi, all over probability that x1 equals A, x2 equals B, x3 equals C, which is then proportional to the probability that x1 equals A given y equals yi, times probability that x2 equals B given y equals yi, times probability x3 equals C given y equals yi, times probability that y equals yi. That's enough. Okay, the probability that y equals yi is the prior, and that's pretty much arbitrary. It has to be given before the evidence is taken into account. So before you know what your features are, you have to have some idea of the likelihood of the different classifications. Make sense? So if you want to put this in context at all, maybe if you're trying to like identify an animal and this is like number of legs and color and how fast it can run, then you have to have some equal probability that before you even know any of those details, it has equal probability of like being a giraffe or a dog. Or if you're in a zoo, then maybe it's more likely that it'll be a giraffe than a dog. So you have to define that prior probability of classifications before you start doing this.
This is a 1 point.
Yeah.
When you say you're trying to maximize P of y equals yi, is that just to say find the yi that will like maximize that expression essentially.
Yeah, yeah. Because this stuff is all staying constant,
Yeah,
right? Yeah.
Yeah.
And putting it down into this form here can be nicer because that way, if you are like, if you just know these three values, then you can just calculate them separately rather than try to do one giant calculation.
So you said P1 is why it's the prior, because it's stuff we already know, like it's knowledge we already have.
Yeah,
Okay, and the evidence is, what is considered the evidence, like the features?
yeah, the features. So note that like, if you're trying to maximize the whole thing, you don't need to find like these three values, which can be hard to calculate because they're like big joint probabilities. You just need to find these three smaller dependent probabilities.
So we're essentially just throwing away the denominator and the
Yeah, yeah, pretty much. Yeah, because the probability that you get that particular set of features is going to be equal for no matter what classification you choose. Okay. Cool. So it's 12:55. We did a lot of information. Well, not as good as Jessica doing it, but hopefully you know some information.
Oh, and you split it up because of the independence assumption in the last
Yeah.
one.
Yeah.
Any chance someone can always figure out why exactly someone lost exactly the number of points they did for instance, just because they had to decide it.
Yeah. I did hang out for a couple Okay. Yeah.
Thanks for doing this.
Yeah. Hopefully it was helpful.
Double